This is my video lab report for Lab 4, Oscillations. The purpose of this lab is to understand and predict the motion of a mass swinging in an arc while also oscillating on a spring. Here are some relevant physics principles that were relevant to this lab. For starters, we have Newton's second law. Newton's second law directly states that the net force is equal to the mass times the acceleration. We also know from Newton's second law that the net force is equal to the change in momentum over the change in time. The force of gravity near Earth's surface can be calculated by taking the mass times the acceleration due to gravity, which is 9.8 meters per second squared. To calculate the spring force, we take 1/2 times the spring constant times displacement squared from equilibrium. And then to calculate the energy principle, we say that the change in energy of the system is equal to the work done on the system by the surroundings and a heat calculation. And then what's relevant to our experiment is the system is the mass, the spring, and the earth, and the surroundings are negligible. There should be nothing in our surroundings. The key takeaway from our experiment is that if we assume there to be no external work done on the system by the surroundings, the change in energy should be zero. However, in reality, it is very difficult to include everything that could do work on the system in the system, so the change in energy will likely be a non-zero value. For assumptions, we ignored heat and we ignored all forces that could possibly be acting on the system in the surroundings, except for gravity and the spring. And we included the Earth and the spring in our system. So this leads us to say that the change in energy of our system should be zero. And then we are also only considering two-dimensional motion. We are only considering motion in the x and y directions. We are ignoring the z directions. This is the video that we uploaded into Tracker in order to get experimental data for this experiment. In order to create our computational model, we had to start with initial conditions. So the mass was found to be 0.402 kilograms, and that was uploaded into this. Additionally, from our tracker data, we were able to find the initial position of the mass, and then the initial velocity of the mass is just the zero vector since we are saying it is starting from rest. For the second part of the computation model, we had to calculate the spring length and the system energy. From a separate video on Chemist, we were able to find the spring constant to be 6.83 newtons per meter, and this was calculated using the period of oscillation. We also know the length of the string that's holding the mass to be 0.70 meters, and we were able to calculate L naught to be 0.123 meters, which is the relaxed length of the spring. For the computational model, the last part we had to do was edit the motion prediction loop. And in doing so, we had to find the force of gravity, which was just the mass times the acceleration due to gravity in the negative y-hat direction. The force of the spring was negative of the spring constant times the displacement. Kinetic energy follows the equation 1/2 times the mass times the velocity squared. Potential energy near Earth's surface follows the equation mass times the acceleration due to gravity times the change in height. And then the spring potential energy follows the equation 1/2 times the spring constant times the displacement squared from equilibrium. And then finally, we had to find the change in energy, which is just the final energy value minus the initial energy value for total energy. Now, looking at the observed motion versus predicted motion, our experimental data is graphed in red and our computational model data is graphed in blue. Similarities between these two are that periodic oscillations are observed for both datasets with nearly identical frequencies. The amplitude range is similar for both datasets, showing that the model captures the scale of motion accurately. For differences, however, the experimental data has slightly smaller amplitudes, possibly indicating energy loss from the system, and since the Y dataset for the experimental data lies slightly below the model curve, the deviation suggests calibration error in the experimental setup. Possible source of error is that in the model we are assuming that there is no external work being done in the system by the surroundings, and we are assuming the change in heat to be negligible. But in reality, this is likely not the case. Also, in Tracker, the center of mass may have been slightly inaccurately calibrated. The first conclusion question that we want to ask ourselves is the energy principle satisfied? Well, if we look at this graph that we were able to take from our computational model that shows the change in energy versus time, the energy principle is satisfied. There is no external work or work in the surroundings being done on the system, and we are ignoring heat. This means that the change in energy should be zero according to the energy principle. And then if we look at the orange line right here, it depicts the total change in energy, and it remains constant at 0 throughout the simulation, showing that the energy principle is satisfied. The last things we had to do in this experiment for our conclusions were calculate the spring constant using both the x data and the y data for period estimations. We had to take the period of the x data and the period of the y data, and then use the equation for the spring constant to get both the x and y period estimations. Thank you.